What's up, guys? I'm going to demonstrate how to solve a chemical reaction equilibrium in Aspen Plus. For this example, we're going to consider a multiple reaction heterogeneous system. So that means that it's a system with both multiple reactions and a solid phase. And the problem can be found in chemical, biochemical, and engineering thermodynamics. It's illustration 13.3-1. From illustration 13.3-1, we want to compute the equilibrium mole fractions of water, carbon monoxide, carbon dioxide, hydrogen, and methane in the steam carbon system at a total pressure of 1 bar and over the temperature range of 600 to 1600 Kelvin. We need to find among these 5 reactions that occur at temperatures below 2000 Kelvin the independent reactions that are going to be considered for our chemical reaction equilibrium. You'll need a basic knowledge of linear algebra, how to solve simultaneous reactions using the Denby method, and lastly, you'll also need to know how to solve mass balance equations for simultaneous reactions. What we're going to focus on specifically in Aspen Plus will be to perform a sensitivity analysis as well as plot the results both in Aspen Plus as well as Excel. The first thing we want to do is we need to reduce the number of reactions by identifying the independent reactions among the species. Normally, if there's multiple reactions, you can use matrix algebra to solve them. But for this example, we're only working with 5 reactions. So we're going to use what's known as the Denby method, which can be found right here in section 8.3. So they explain how that procedure is done. Rather than read off what's explained, I'm just going to go ahead and solve the equations and show you how that's done. So to use Denby's method, the first thing we're going to do is break down the molecules into their constituent atoms, starting with water as hydrogen and oxygen. Do the same thing for carbon monoxide, carbon dioxide, methane, and hydrogen. Now in the book, it states that neither atomic hydrogen nor atomic oxygen are present below several thousand degrees. So we're going to go ahead and eliminate them from the equations. So first thing is take E and replace the value of 2H into equation A, and then solve for oxygen. And O gives you H2O minus H2. So now that you have a value for O, replace them in equations B, C, and D, and you'll obtain the 3 equations below, and those will be your independent reactions. Let's go ahead and open Aspen Plus for this simulation. So we're going to go ahead and create a new simulation. So we're going to set our units to be met C bar, and then we're going to go ahead and specify the components that we're working with. Now that we've specified our components, we're going to go ahead and choose the method. Now that we've specified our components, we also want to make sure that we specify that carbon graphite is going to be a solid. And now we can go ahead and choose our methods. Under specification, we want an ideal method, and we're done with the properties section. We can go to simulation. And the simple simulation will consist of a reactor using the R-Gibbs reactor. And we're going to have a material stream coming in as our feed. These will be our products. And because we have a reactor, we're going to go ahead and establish reactions. So the first thing we're going to do is create a new reaction. It's going to be a general reaction. Once there, you can create your new reactions. Go ahead. Reaction class will be equilibrium. Let's call this first one carbon dioxide as the first reaction where carbon dioxide gets, and put the components right here. It's going to be carbon, graphite, coefficient of -1 since it's a reactant, and 2 of water. And we have the products as carbon dioxide, which is this one, and 2 hydrogen. 1, that, and 2 of hydrogen. We hit close, we're complete with that. And similarly, we create the other 2 reactions. All right, now that we're complete with the reactions, we can go ahead and modify our streams. First thing we want, let's go to stream 1. Let's go ahead and choose 800 Kelvin for the purposes of this experiment and 1 bar. And our composition will be the following. We'll have a basis of 1 kilomole of water as well as 1 kilomole of carbon. We can go to the blocks, go to our reactor, specify our pressure to be 1 bar and our temperature to be 800 Kelvin. And now we're done. We can go ahead and run the simulation, make sure we have no errors. We can click next input, no input needed. Let's go ahead and hit OK. Carbon is a solid, yet Aspen Plus included it in the mole fraction calculation. So the way to go about this is the mole fractions reported, they are of the total reaction product and not just the gas phase. So this makes this calculation incorrect. So the best way to correct it, we can copy the data into Excel and manually correct the entries, or what we can do is add a flash separator. So let's go ahead and do that. Go to your main flow sheet, and we're going to add a separator. It's flash 2. Go ahead and click it right here. And we're going to add 2 material streams, one coming from the top, one at the bottom. And we're going to go ahead and reconnect 2. So cancel insert mode. Right click on stream 2, reconnect destination, connect it to the feed. Go ahead and align your sheet, Control B, perfect. So go ahead and open your block for your separator. Notice here, again, we want a temperature of 800 Kelvin and a pressure of 1 bar. Now, because our unit sets at the top was set in metric with temperature in Celsius and pressure in bar, we're always going to have the results reported with these units. So in part 2 of our simulation, I'm going to show you guys how to change that before we even run the simulation by creating your own unit sets. We can go ahead and run the simulation, and it looks like everything is fine. So we're going to go under the results. So go to results summary, click on streams, and now you have the results for all 4 streams, your feed, your product, and the 2 streams that come out of the flash separator. What the flash separator does is it separates your components that are in the gas phase from those that are in the solid phase. And in this case, we see that stream 3 contains all the components in the gas phase, and stream 4 contains the components in the solid phase. Now, we are interested in getting the equilibrium mole fractions. Now, normally you can set that up under report options before running the simulation, and it would give you your mole flow as well as your mole fraction. But I'm going to show you guys how to do that one time in case you already ran the simulation. So go ahead and go to Streams Custom, right click Default, click Add New. You can name the sheet whatever you want, click OK. Right click Sheet 1, go to Edit View. We're going to select all the streams since we're interested in getting the mole fraction for each of one of them. And we want the component mole fraction. So go ahead and click on that. You can also move it up since we're interested in it. We can put it right underneath mole flow. Hit next. Everything else should be okay. You hit OK. And once you do that, you'll notice immediately that your mole flow is the top at the top and your mole fraction is right underneath. And this is what we're interested in. And sure enough, we have our values for the simulation. Let's go ahead and save our simulation. We're going to go ahead under File, Save As, Compound File. All right, and part two, I will show you guys how to run a sensitivity analysis in order to graph the results.